Right, question 14. It's applying Newton's laws of motion. Right, this is a Newton's cradle, by the way. This is a piece of kit that was designed and invented by Sir Isaac Newton to demonstrate conservation of momentum. But anyway, it wants us to apply Newton's three laws of motion. Now, this is a skill that's examined quite a lot, and students really struggle. They really struggle looking at something and being able to see where and how Newton's three laws of motion apply. So this is something that I think we need to practice. Right. So just to run through the three laws, well, the first and second laws are kind of like this. They're two versions, or they're the same law in two different scenarios, aren't they? F equals ma. Now, in the first law, if the forces are balanced, F is zero, so acceleration is zero. All right, so an object will remain at rest or in uniform motion unless acted on by an external force. That's Newton's first law, or N1. If you're going to do a question where you apply Newton's laws of motion, rather than having to write out Newton's first law of motion, Newton's second law, write down, abbreviate them to, because it does this in the mark scheme, there's absolutely no reason why you can't abbreviate them to N1, N2, and 3. The examiner will know exactly what you mean. Okay? Right, so what's N1? N1 is when the forces are balanced. That means acceleration is zero. N2 is what happens when the forces are not balanced. We get acceleration. And N3 is reaction and action happening, which are equal and opposite. But don't forget they happen on different objects. Right, so let's have a looking at the mark scheme, quite straightforward. Right, it talks about the collision between A and B. You could quite. I certainly would have given you marks if you talked about, well, this A is going to accelerate, isn't it? Newton's second law rather is going to apply to A as it falls just after being let go. Now, the weight of A is vertically downwards, but there is a component of weight that's always perpendicular to motion, isn't there? So that component, that component that's perpendicular to the wire, that's the component is in the direction of the motion. That's going to cause acceleration. So that's where N2 would be applied. So there's going to be a component of the weight of A that's in the direction of the motion perpendicular to the wire that's going to make A accelerate. And that's why it accelerates. That's why it speeds up from rest and hits B with a certain speed. Okay? It's because of Newton's second law of motion. Right, during the collision, what's going on here? Well, the first thing that happens is A hits B with a certain force, so B hits A back with the same force in the opposite direction. Here we have Newton's third law being applied. Okay, if A hits B, because A hits B with some momentum, it exerts a force on B. Now B is going to exert exactly the same force back, so we've got N3 in action. Okay, but at the same time, we have N2 again, don't we? If B exerts a force on A in the opposite direction to A's motion, it's going to slow it down to rest. It's going to cause it to decelerate until it stops. So we've got Newton's second law, or N2, in action. At the same time, at exactly the same time, A is exerting a force on B. So B is going to accelerate in that direction. So B accelerates from rest and is given some kinetic energy. So there's actually three things we can talk about there, can't we? During the collision, we've got Newton's third law. They're both exerting forces on each other, but we've got A accelerating B, and we've got B decelerating A. So we've got two applications of Newton N2 and one of N3 there. Okay? And then B's going to rise up. Okay? You could talk about N2 as B goes up, couldn't you? just like we've got the accelerator, the component of weight that's parallel to the direction of motion, we've got a direction of weight here that's going to be decelerating B, can't we? We can talk about that one. There's always going to be, as B is rising up, there's going to be a component of B's weight that's going to be decelerating it. So there we have again N2 being applied. So quite a lot you can talk about there, but it does require some decent, well laid out, clearly set out explanations. Always think about the flow charts that have had you been doing over the past year. Okay, think about what happens next, what happens first, and what happens next. Okay, cause and effect. Think about cause and effect. Okay, so there you go. Applying Newton's 3 laws of motion. Right, last little bit is the calculation. It wants the momentum of A just before it hits B. This is easy. It gives us the mass. Okay, all we need to know is the speed at which A hits B at. Okay, so it kind of, like I said, it signposts the question a bit here. Now it tells you to take measurements from the diagram, from the photo. So if that's 11 centimeters, then it wants you to use your 30 centimeter ruler and to measure on the diagram. Okay, try and get the center of mass here. So A starts at that height. A finishes at that height. You're going to use your ruler, your 30 centimeter ruler, to measure that height there. Okay, now according to the mark scheme, I've got this just as on my screen. I'm not sure how you did that, but I'm sure you managed. Okay, that gives you a height of about 6 centimeters, 6.6 centimeters. Okay, or let's get this into meters because we're going to use this in a calculation. 6.6 times 10 to the minus 2 meters. Okay, makes sense. Right, it's energy now, isn't it? The loss in GPE is the gain in KE. Okay, we can ignore air resistance. Does it tell us that? I think it might do, or we can maybe just say we're going to ignore air resistance. So the gain in KE is from the loss in GPE. So the loss in GPE, but you will always write that. You know, the examiner wants to see your thinking, so why not write, okay, loss in gravitational potential energy is equal to the gain in kinetic energy. Okay, so potential energy, we've got the mass 0.022 is the mass. G's 9.81 times 6.6 times 10 to the minus 2. Okay, so that's the loss in GP. That equals a half times the mass times v squared. Now, if you write it out like that, that's quite nice because, as we can see, they cancel from the calculation quite efficiently. So then we've got, or left with v squared is 1.29 and v is equal to 1.14 meters per second squared. Sorry, meters per second. And then we're just calculating momentum. Don't forget, how could you forget? Momentum is mass times velocity. 0.025. Not forgetting the unit for momentum, which is kilograms ms to the minus 1. Okay? Right, apologies for Cami not being very happy at the moment. Anyway, right, hope that made sense. Again, not that scary once you get into it and kind of think it through logically. Thank you very much.